Eitan, who's visiting as a professor in the Buchmann-Mehta School of Music at Tel Aviv University. He received his PhD in music theory from the University of Pennsylvania. And after doing visiting scholar stints at Northwestern University of Arkansas and Harvard Universities, Zohar joined the faculty of music at Tel Aviv University. Zohar's research, I think, exemplifies true interdisciplinary scholarship, merging a deep understanding of the principles of music theory and structure with an equally deep understanding of the properties of the human perceptual system and cognitive system. Zohar studies music perception and cognition, examining the ways in which music perception and performance draw upon cross-modal or cross-sensory correspondences between properties of musical form and perceptual features and other modalities such as vision, and then examines these correspondences as a way they might underlie our understanding of musical metaphor. His work ranges from topics such as how we interpret and understand musical structure and thematic relationships in music to how we experience absolute pitch and mechanisms underlying other aspects of auditory perception. So I won't go on, but I just want to say that we're very fortunate to have Dr. Eitan here today. His talk is entitled Space Oddity, Musical Syntax is Mapped onto Virtual Space.
Thanks, Lynn. You wouldn't see this because of the mask, but I'm blushing. And thanks for the entire CMBC staff for the beautiful hosting and efforts. As you can see, this is sort of an odd paper. And let's get it on. Where is it? It is. All right. This is a collaboration between Netta Maimon, who has just completed her PhD work in psychology at TAU, and is attending now and may answer most of your hard questions that I wouldn't be able to answer. And Dominique Lamy of the School of Psychological Science at TAU, and myself. We're going to show that musical syntax is mapped by listeners onto aspects of actually perceived experience space, like spatial position, up and down, left or right, distance, or object size. And we're going to show that this mapping may be implicit and they do not require any conceptual knowledge of music. People don't know any musical terms and have never had musical training, perceive musical syntax in terms of space. And we also often contrast with the metaphors and concepts and theories and spatial models that musicians use. They don't derive from them, but from some other domain. So we start from something that most of you probably know better than me. We have quite a lot of different, sorry for this misspelling, quite a lot of data that indicates that we perceive and think about abstract concept and schemata in terms of physical domains, particularly space. So I guess everybody knows Lakoff and Johnson's work. So here are a few examples from Lakoff and Johnson of how we map vertical orientation onto different abstract domains like mood, state of consciousness, moral virtues, that has social status, and so forth. And we also have quite a lot of behavioral experiments that indicate that this mapping actually affect important aspect of our cognition, like memory, attention, learning, and so forth. So again, given an example from a specific mapping that would be important for us later on in the lecture, vertical position up and down and balance, a good and up metaphor can affect the way we recall memories, the way we record autobiographical memories, the way we recall recent memory of position, and so on and so on. And there is an emerging work in neurophysiology that suggests that the brain coding of abstract scheme works in a way which is similar to the way we encode space, physical space. And I guess both of you, Danny especially, would have things to say about this later. Anyway, here we examine whether such special mapping of abstract domain apply to the syntax of Western music, and specifically whether syntactical function in music may associate with vertical and horizontal position, with distance, with centrality, and something being at the center of the field or at the periphery, and with object size. And we do this with both with musicians and non-musicians who have no clue about musical concepts. And we apply explicit and implicit behavioral measures that I will tell you about soon. But first, what is tonality and why it makes sense to examine its spatial mapping? Okay, so to really understand tonality, my advice is enroll into your music department and stay there for at least 3 years. But now we have about 3 minutes for this. So a few words and a few sounds. Tonality structures a relationship among tones and among chords, collections of tones in minor and major keys, which are the framework for most of Western music, classical and pop and rock, in the last 3.5 centuries at least. And an important concept regarding tonality is tonal stability, which means that some tones and corresponding some chords are more stable than others in the sense that they're associated more with closure, with ends of units, while unstable tones are associated with continuity. We expect them to go somewhere else. And unstable tones and chords may convey some tension, and they imply resolution by quote unquote moving, and note a special metaphor, to neighboring stable tones. And all of this is centered around a specific note and chord. Usually if we're in C major, it's C. If we're in E minor, it's E, and so forth, which is the most stable and the most closure tone in the system. This one. Okay, now we can talk about a specific hierarchy of the tones in the scale. Here you see 1 octave scale with the tones numbered from C to B. And it can be transposed to other keys, of course. The most stable, the tonic scale degree 1. And 3 and 5, these are the other notes of the tonic chord, are also relatively stable. The other scale degrees here in white are less stable and tend to resolve, proceed into the stable tones. And finally, you see the black ones. These are out of key notes or chromatic notes, as musicians call them. And they're highly unstable, and they don't fit there. So they imply motions to the diatonic, to the one of the 7 degrees here. Let's hear how it works in a very simple way. Okay, that's the scale. That's the tonic note. And here's the tonic note with the other stable degrees, 3 and 5. And now the unstable diatonic degrees resolve to the diatonic degree. And finally, those odd that's it. Now you know everything you can know about tonality in 2 minutes. I told some of you yesterday that I worked on these 2 slides as much as I worked on the other 30 something. Oh, don't start again, please. What did I just do? No, okay. No, please stop. Okay. Okay, good. Now, another way to address tonality is that it shapes probabilities within a music written in a specific key, and hence it shapes listeners' expectations. So it shapes probabilities on various levels for the rate of occurrence of each note in the scale, and more important, and stable tones are more frequent than unstable tones. Also for specific successions that are more likely than others. And for instance, unstable tones tend to, as we hear, proceed to their more stable neighbors, and not vice versa, less vice versa. And also for where specific notes or specific sequences of notes or chords will likely occur within a musical unit, musical phrases. So in the beginning and middle and so forth. And especially there are specifically stylistically codified sequences of chords that move towards the tonic, this more stable note, which musicians call cadences. And this is a term that is also a special metaphor. It's derived from cadere, which is falling down in Latin. And we had one of those few slides before. Okay, now a few words about the huge subject. I could actually present an entire class about it. Tonality is not just a topic that was speculated on by music theorists. It was, but in recent decades, there were quite a few empirical studies, both behavioral and neurophysiological, that establish that generally what I just said is cognitively true. People, including people who haven't studied music or know its concept, but have listened to quite a lot of Western music, probably through statistical learning, respond to tonality in a way that is consistent with basic tonal theory. And I won't go into it, just say that some of these methods were explicit, like asking somebody to continue a melody, or asking somebody to what degree a note fits a tonal priming, and some of them were implicit, including, for instance, ERP measures, and so on. Again, this is for another lecture. Just to point out that tonality is a cognitive schema. Now, musicians, as we have just seen, discuss tonality mainly through metaphors of space and motions. For instance, we talk about tonal center, which is the tonic, the most stable tone, about living tone, the tone that resolves to the tonic, out of key or within key notes, a cadence, which I explained is from falling, unstable tone, which moves towards stable tones, harmonic progressions, sequences of chord move away or towards the tonic, and keys are either close or remote from each other. Now, this is not surprising because we use space metaphor for almost everything, but we would expect, as we found in other domains, that these metaphors would, at least for musicians, affect the actual mapping of tonality onto space. And especially space and modal mappings are also historically important. If we go back to Jean-Philippe Rameau, who was the first major theorist of tonality, he talks, for instance, about tonal relationship in terms of gravity, of course, in Newton. And here's something I'm not going to talk about, just 4 examples of different geometrical models of tonal relationship. Each one is related to a different theory. Each one expresses a different relationship. This one, for instance, sums up the finding of Carol Krumensel, a psychologist, regarding the associations between tones within a key, just what we talked about, stable and unstable, and it addresses basically similarity between them, perceived similarity. Here are ours, but what I want to talk about, what I don't want to talk about is something that all these models share, and which is very obvious. They're not literal. I mean, they're metaphors. For instance, this geometrical model by Krumensel doesn't actually say that this pitch, C sharp, is perceived as higher and to the left of that pitch, F. Of course, different similarity relationships and onto space, it doesn't actually talk literally about space. So, but that's exactly what we are going to examine. We are going to examine literal associations between tonal stability, the tonal hierarchy that we described before, and perceived physical space. For instance, weird questions like, are stable tones like the tonic perceived as they are above or below unstable ones, or to the right or to the left? Are they louder or smaller, and so forth? So that's why this is entitled Space Oddity, which is Mehta's ingenious title. Okay, so if we go, I mean, music theorists and musicians talk about map tonality onto space in various and sometimes contrasting way, but if we just look at the most common and important, we can derive 3 hypotheses from this musical discourse. One is distance, which says that simply that the perceived spatial distance, how far we perceive different tones from each other, spatially, not metaphorically, reflects tonal stability. For instance, unstable tones, like chromatic tones, will be farther away from tonic than more stable tones. So that's one hypothesis. Another one relates to the metaphor of gravity and to terms like cadence and so forth. And it suggests that we will associate stable scale degrees with lower spatial positions. And the third one derived from terms like tonal center and from all kinds of models of tonality where the tonic is always in the center, is that suggests that stable scale degrees, especially the most stable, the tonic, would be associated with the central locations in space and unstable ones with the periphery. Okay, so just what I think is new with regard to both exploring cross-modal correspondences and exploring metaphorical mappings in studying tonality. First, okay, another spelling mistake, sorry. There are lots of studies, empirical studies, that examined how basic perceptual auditory dimensions associate cross-modally with visual or tactile dimensions and so on. For instance, we know in different ways that pitch that we call higher, which is actually not higher, it's a metaphor, is actually perceived as higher in space than lower pitch. And it's also is to the right of lower pitch, and it's smaller and so on. But here we explore a different type of cross-modal correspondences between space and high-level syntactic structure, not between two basic perceptual dimensions, but between perceptual dimensions, in this case, relating to visuospatial perception, and syntactic structure as it applies to music. So we ask whether musical syntax per se, rather than pitch height and or other basic perceptual domains, can engender specific spatial visual connotations. And also, another thing which was interesting for me is looking at two groups. One group is a group of trained musicians who habitually use all these spatial metaphors, know tonal theory. They have a conceptual baggage. And that group is of non-musicians that have no musical training and have no knowledge of the concept of music theory whatsoever, but don't know anything about these spatial metaphors and so on. So by exploring both groups and comparing them, we can investigate whether and how explicit conceptual knowledge of an artificial domain like tonal syntax may affect these spatial mappings. Okay, so we use basically two paradigms. Both are derived from well-established paradigm with experimental paradigm with some changes. Let's see what we did. Experiment one. A very simple task. Very confusing for most people, but simple. People hear a sequence of chord that establishes a key and then a specific probe tone. In each trial, a different tone. All the 12 chromatic tones were heard several times. By the way, the strange sound that you hear is shepherd tones, which is supposed to minimize the effect of pitch height. We want to control the it is all very, very ugly, so I apologize. So what we ask them, just locate this final tone in this grid, just the way you feel it. Just do it. And they just would do that, for instance. Another trial, and they may do this. Okay, that's the experiment, lots of trials, lots of blocks, and so on.
Ignore the first three.
What?
I'm supposed to essentially ignore the first three, just judge the last one.
Just the last one.
Okay.
Just the last one,
Do
yeah.
it again.
Yeah, I think
It's fine.
I can let you do the entire thing. Okay, so I'll just, implicit hypothesis number one suggests that there will be some actually negative correlation between the distance of a tone from the tonic and its degree of tonal stability. So what did we get? That's all Mehta, all the animations are Mehta. Okay, we received pretty good correlation. What did we do actually? The y-axis is the distance from the tonic. The x-axis is based on another experiment in which other participants, both musicians and non-musicians, had to rate This is based on a very old paradigm by Karl Krugman, who had to rate how well each of the probe tones, the tones you had in the end, fits its tonal context, that is, how well it fits the free chords that preceded it. And we correlated this, and as you see, this is scale degree 1, the tonic, of course, a distance 0 from itself, the highest rated. And this is dominant scale degree 5, also very stable, a relatively high rating, and the closest to the tonic. To musicians, there will be a few surprises here, but generally there is a pretty good correlation. You see for both major and minor key, with basically the more distant a tone would be from the tonic, the lower its fit rating, but it's the less stable it will be. So good for hypothesis 1. Now, hypothesis 2, where suggests that following the gravity metaphor, stable tones would be at the bottom, unstable tones at the top. And number 3, centrality, stable tones at the center, the least stable at the periphery. That's the way Karl Krugman has it. And this is the data. Major keys here, minor keys here, and just look at this side. These are the most stable tones, 1 and 5, the 1 tonic, the dominant. They're not at the bottom, they are at the top, and they're not at the center, they're at the left. The same thing for minor keys. And what we find at the center and at the bottom are not the stable tones, but quite unstable chromatic tones, both with flats and sharps near them. So we got results, and these results are shared by musicians and non-musicians. There's no interaction. Here's actually the the box plots for the y-axis. Musicians and non-musicians, slightly different patterns, but there's no significant difference between the groups. And the stable diatonic tones, 1, 3, 5, are higher, significantly higher than our tones, and they're also significantly to the left than our tones. Okay, now we wanted to examine this relationship in a less explicit way, not giving people time to reflect and to think, not asking them a direct question, trying to elicit more automatic and less introspective and also we use a version of the infamous IIT test, Implicit Association Test. If you know your history of psychology, you know that it was first used to elicit implicit bias about race, gender, age, and so forth. We use it in a politically neutral version that was first used by Spence for cross-modal experiments. So what do we do? We assign to one key at the computer keyboard one musical stimulus, for instance, this, and to the another musical stimulus. The first one I hope you heard, and it's with stability. The second one, instability. And we also assign one visual stimulus to each key. In this case, one was a high circle, and one was a low circle. Now, there are two conditions, two kinds of blocks. In one block, we assign one block is congruent, but it's according to experiment one, the same response key is assigned to auditory and visual stimuli that go together well. So in this case, based on experiment one, the high circle and the stable progressions. And the other hand has a low circle and unstable progression. And this goes for an entire block of stimuli. And then there are the incongruent stimuli where the high circle is assigned to the same key as the unstable progressions and the low circle, which is unstable. And of course, we counterbalance the hands and so forth. And what we expect that if what we found in experiment one, that stable goes with up, unstable with down, is also work at a faster, more implicit level, then responses to the congruent blocks would be faster and more accurate than responses to the incongruent blocks. Hope that was clear. Oops. Okay, so that's one condition. And that's the other. And results. And what we received is basically what we received in experiment one. If you look at the bars are response times, and this is the incongruent condition, this is a congruent condition, and response times are slightly longer than for the incongruent condition than for the congruent, and this represent error rates, and again, incongruent error rates are higher than congruent error rates. Now, only the error rate result is significant, probably because we didn't have enough participants, but as you see, the response time goes in the same direction. So basically, we have this unexpected association of high stable, both explicitly and implicitly. Now, experiment 3 did the same thing, but with left-right. And here, the results are inconclusive, nothing for visual congruence, and we have a significant result, but in the opposite direction of experiment 1, that is right is stable for the auditory stimuli. So lateral direction is, but still these are shared by musicians and non-musicians. So lateral direction is less conclusive than up, down. And finally, we examined size. First, explicitly, what did we do? People heard the same sequences of a number of chord and then a tone, and then they had to match each tone with one of these circles. And there were two ways the circles were arranged, this way or that way. So what we found, we first found a highly significant correlation, association between size and stability. Stable tones were larger, but when we looked further at the results, we saw first that this was true only for musicians, and this was true only for musicians when when the large circles were to the left. So only this interaction worked, but as you see here, these are the means from 1 to 7. It's highly significant, and we'll try to interpret it later. And nothing in the implicit experiment, the IoT experiment. So this is a summary of what we found. Tonal stability is negatively correlated with spatial distance from the tonic, which confirms hypothesis 1. It is not associated with centrality in space, which refutes hypothesis 2. And it is associated with higher position, both explicitly and implicitly. And this is in contrast with hypothesis 3. And it is associated with left explicitly, but not implicitly. And it is associated with larger size explicitly only, but only for musicians and only when large is left. And why I talk about such a triple interaction at all, because it's so strong. So there is something there probably. Now, how do we interpret it? First, let's try to interpret the most robust finding, which is the vertical association. So this is what musical discourse would suggest, and it is wrong. But this is what valence mapping would suggest. And if you remember our examples from half an hour ago, I hope it's not more than half an hour, then there is a very strong association between positive valence and up and negative valence and down. And what we speculate is that what we found is due to mediation of emotional valence. That is, stable notes sound more expected, calmer, more pleasant to most people. So they're positive, so they're up. So that might be, the speculation should be examined further. That might be why they're mapped in this way rather than according to musicians' metaphors. And for horizontal position, we got mixed results, but still I want to point out something that may interpret the explicit results, that stable is left. If you look at the musical keyboard, which is something that everybody, including non-musicians, know, the low tones, which are stable in various ways, are usually longer. As the bass note that support the texture, they fall on the downbeats more, they're less ornamented, and so on, are to the left. Here's a nice musical example that you probably know. This is Rachmaninoff's prelude in C-sharp minor. Well, it's hard for me to stop. It's beautiful, but it takes 7 minutes, and you're invited to listen to it later. Okay, so what we can conclude? We can conclude that musical syntax, that is, tonality, is mapped by listeners onto some aspects of physical space. We can conclude that some of these mappings do not require conceptual musical knowledge, and they're revealed both explicitly and implicitly, or perhaps automatically, and that for both musicians and non-musicians, the perceived spatial mapping of tonality differ, sometimes contrast with the mapping that are implied by metaphors and verbal discourse and geometric models of tonality. And we think that the most robust mappings are mediated by emotional balance, but this is a speculation, and by musical practice. At this stage, this is a speculation. And okay, I won't go over this with some of our other experiments. So we examined, for instance, brightness, and we examined facial expression. What you can basically conclude from all this is a support of the mediation of emotional violence. Wherever emotional violence seems to be effective, we got robust results. Now the significance, I think, we have a new type of cross-modal mappings that is syntactical functions mapped onto perceptual dimensions across different modalities. We explore a source of referential musical meaning, how music can refer to non-musical words, simply by its abstract musical structure. And we show that perceptual mapping of abstract domains, like music, may be independent of the verbal metaphors that underline this domain. They may be related to other types of verbal mappings, but we can talk about a domain in specific ways and think about it non-verbally in just the opposite way. Okay, thank you for daring to come here. And I really want to thank the entire staff of the CMBC for beautiful hosting and lots of help, and for teaching me lots about high tech today. Yeah. That's it, Tamara and Lynn and Dit. Thanks a lot. And of course, I want to thank Netta, who may be still attending, and Dominique, who is not, who gave me, as a musician who really doesn't know much about psychology, lots of support from the other side. Okay, thank you.
Your finding about the vertical, so that one is different from the musical metaphors in the literature, right? Yes. And it's also actually different from the real physical scenario where most objects have, so the more stable the object is, the lower the position, basically, for a center of mass. So I wonder whether you think about replacing the lower and the higher circles with shapes that actually show the instability. So, for example, a stable shape versus an unstable shape.
Good idea.
Like whether you can find that.
Good idea. Yeah, it's a very good idea, and well, we should explore it, or maybe you should. Yeah, but yeah, that's an excellent idea, because actually here we only indirectly derive this conclusion, and we didn't present to them visually the metaphor of stability. That's something to look at. Thank you.
Yeah, great talk. So the valence explanation, right, seems to work well for the vertical. And other people have shown, Daniel Casasanto and others, right, that more positive valence things are higher than lower valence things. How do you explain the horizontal mapping, though, where you have the stable one, which is presumably more positive, right, going to the left? Okay.
Of course, this is all speculation, but I think a part of it is the musical association that I use, that stable tones tend to be at the left in musical keyboards, which is the most common musical instrument, everyone knows. So that's one possibility. Also, I would note that these are Hebrew speakers and writers. So as you know well, you work in this, the mapping of right and left into various dimensions tend to be a bit confused with Hebrew speaker because of writing direction. So it may be also applied to this mapping.
Yeah, that's interesting. Because at least Daniel Casasanto would suggest that positive, at least if you're right-handed, right, where that side of your body is more dominant, would go to the right compared to the left. But maybe here, more positive is in relation to
so
reading
maybe here people associated the left and right to musically specific practice, but I can only speculate about this. And also what we've got is left is explicitly associated with stability in the explicit paradigm, but right is associated with stability in the implicit paradigm. So it could be that when people had time to think about it, they imagined music and worked that way, and when they didn't, then the right side would be the positive, and then violence occur. But I mean, it's just speculation, of course. What they can.
So just to follow up, they're mostly right-handed, right? They're not mostly left-handed.
Yeah.
So what if you asked the Hebrew speakers to do something like what Casasanto does, right? Which is you have a set of positive things and a set of negative things and just sort them, right? So at least English-speaking right-handed individuals would put the positive things on the right and the negatively valenced things on the left. But maybe here for stability with respect to music and other things, you guys put the positively valenced things on the left and not the right.
Yep.
And
also,
maybe that would explain it.
Also, I'm only half joking here. This is an academic community, and could be that which justice here is most liberal. But so I don't know if I'm joking or not. Maybe I should be serious. Maybe well, I tend to associate right with very bad things. So I don't know if anybody has looked at it, but this could be another factor.
We've looked at it. The scientific community, right, has looked at it with English speakers. But I think it's an open question whether that horizontal space to valence mapping is flipped when you read it in a different direction.
I just don't know, and what we've said are very strong and conclusive results with regard to verticality and inconclusive results with regard to right and left. I mean, very significant one way in the explicit paradigm and in the opposite way in the implicit one.
Oh yeah, well, I'm also intrigued by this stability and instability in a horizontal space. That implies that everybody visualizes some kind of keyboard, you know, where low sounds are on the left, high sounds get on the right. So stability somehow implies it's associated with a lower register and instability with a higher register. But what if you're not visualizing the keyboard, but you're visualizing the musical staff, which is then vertical, not horizontal? Or you're a string player or a woodwind player where, you know, it's not a horizontal layout, how they think about pitch.
I can, do you hear me?
Yeah, I hear you.
Okay, I can answer that as a cello player, and actually as a cello teacher, as a cello teacher, where the higher notes are actually lower in space, if you imagine the cello. So actually the low is low and high is high, and low is left and high is right, is really strong in children also, and in all players of any instruments. So when I teach the cello and I say the higher notes are actually lower in space, then the children are quite they don't they get confused. So I think the left and the lower register is quite common in musicians, even if some are on the opposite directions.
Okay.
Excellent. Yeah.
Zohar, I'm trying to understand the stimuli. So you, in the beginning, you talked about pitch, and then you talk about the structure, right? You were saying that you've got this new cross-modal correspondence in structure.
Yeah.
And not in pitch, I suppose.
Yeah, not in pitch height. I mean,
so you presented in the stimuli 3, and part of my ignorance to all the musicians, 3 notes or something before the target.
Yeah.
Okay. What was that to do? What was the purpose of these 3 things before the target?
Oh, okay. That was a prime. These 3 chords prime listeners to structure note in terms of a specific key.
That's to provide the structure.
They provide the structure. Yeah. And then, I mean, the thing is that the same pitch, the same note can be very stable in one key and very unstable in another key. So to understand the structure, you must have some kind of priming, either maybe playing the scale up and down, or playing a few chords like we did. And there are lots of works that establish that this bit of priming already established cognitively the tonal structure for most listeners. So that was
so in these same subjects, if you didn't put that structure and just gave the target, what's their rating?
Just get one note.
Yeah, just the target. You ask them to do it high or low. What happens?
Okay.
You get to say. My question, dude, is asking whether the structure is even working.
Yeah. If you just
and you're not showing anything other than I don't know what. Right?
The reason we don't show anything without the structure is that there are dozens of experiments that show the mapping of pitch height. If you just have one note without context, then you respond to its pitch height, or maybe sometimes to other basic perceptual dimensions like its duration or loudness. But what we did, we actually had the same notes, the same probe tones, final notes presented in with different priming, but gave them just the opposite significance with regard to tonality. And when you look, we don't have this spine here, but when you look at the results, you can see, and this is very expected, nothing new. That's why you can see that the same note, when it is primed, like the note C, when it is primed by a sequence of chords that suggests the key of C major, would be judged as stable. And if the same note C is primed but by a sequence of chords that suggests the key of F sharp major, it would be judged highly unstable. But this is all news. We know that. We need the context. Tonality, like any kind of syntax, is how an element relates to context. And these 3 chords give you the context.
So just so I can get this straight, with that structure, so without that structure, just pitch would be the complete reverse. That note would be high in just a pitch judgment, for example, right? But
not the complete reverse, but
flips.
Not the complete reverse, but people would map the notes according to pitch height. which we didn't hear. Like high notes would be met. High and
That's right, and you didn't get that in this
we
one.
didn't get
and
that
that's
at
the
all.
claim.
I mean, we got, that's where we're not related to pitch height at all. Also, we had some acoustic manipulations to prevent the pitch height from interfering.
Okay, good, thank you.
I'll stand up. I had a similar question about the methods. When I see these, and when you ask me to judge the spatial position of not even just a tone, but of a tone given a context elicited by three of the chords, I feel like I would be guessing a lot of the time. How consistent are these results? And how did you actually calculate those specific positions on the plot you were showing us where you had that two-dimensional space?
Okay.
You were showing a single value.
What I learned from my own work and from other people's work is that often participants would go out of our experiment and say, we don't understand what you did, we just guessed. And when you analyze the results, you see that might have guessed, but they guessed in a very specific direction. This, I guess anybody who has performed perceptual cognitive experiments had this experience. Now, what we did is very simple. They had the cursor, and they had this sequence of chord and then the note, and then they had to move the cursor to whatever they felt or guessed or whatever they want to call it, position that fits this note. And many of them said, "Who? How can I know that? I mean, musicians had ideas, but they actually acted differently from their own ideas. Non-musicians just thought it's a very weird thing, and a thing that just thought I'm going to guess so that I finished this experiment and get my $10. But when we analyzed this, we saw that they didn't guess randomly. That's what the data says.
Yeah, sure. I guess I get that it's not random. I was just curious about how much consistency is there, both within individuals. Like if you gave me the same stimulus, me and Danny the same stimulus, on average, we wouldn't be completely.
There's lots of noise, but there is enough consistency to make some of this result highly significant. Of course, there is a lot of noise. I mean,
so I can. Can you hear me again? I think about the two-dimensional space that you saw. So the standard errors are between participants. So each participant dot is actually, I think, 12 repetitions. And this is not calculated in the standard error in the two-dimensional space, but the analysis was linear mixed models, and we inserted the within participant variance into a random slope. Does that maybe answer a few of your questions?
Yes, on a statistical level, that makes sense.
Yeah.
I was just kind of curious, like from a visual point of view, if I'd seen all of the individual responses, would I see really tight clusters or a big diffuse blob of responses, which over enough averaging turns out to be the pattern that you were showing? But I've asked too many questions. I'll stop talking.
Yeah. Netta gave the statistical explanation, which is much better than I could do. But more generally, I mean, do you know of many cognitive experiments without lots of noise? No. Yeah. So there is lots of noise here, but it's not totally random. That's why it's significant. That's all.
So Charlie is asking about the priming that we used, the element that we used. So we heard the progression of the cadence, but we actually used two types of progressions. One is the cadence, and the second one is just the priming of triad. just a triad chord, and in two different keys.
Yep.
Does that answer your question, Charlie?
Okay.
I think,
Okay, so
I think we're good, and thank you so much for your talk.
thank you all for coming. And if you have additional questions, then you can just write me.
Yeah.
Great. Yeah.
Okay, thank you.